My name's Russ Harmon. I'm a full-time software engineer here at Google, like I think most of you as well. And thank you for coming. This is Morten Kromberg. He's the CTO of Dyalog, which is an implementation of a programming language. Let's get started.
Okay, well, thank you for coming. And thank you, Russ, for believing that they would come and inviting me to come and give this talk about something which is definitely not mainstream. In fact, Dyalog is an implementation of an ancient programming language called APL, which I think is now 52 years old. And I have been using it for about 36 of those years. And I remember I did a similar talk previously where a guy came up to me afterwards and he said, "You've been using the same programming language for 35 years and you're still happy?" As if that was completely impossible and unthinkable. So I sort of started off, as a young man should. I spent the money I'd made selling newspapers or delivering newspapers and buying this do-it-yourself kit. I soldered all those integrated circuits onto a board, and I got this thing to work, programmed it in Z80 bytecode. I'd never soldered anything before, so it would only run for about 3 or 4 minutes before crashing. Then things got a little bit better. I found, Commodore started making these really nice machines. I learned BASIC. And so things were going fairly normally until a friend of the family one day brought me down to the place where he was working, and he said, "We're using this thing called APL," and he typed this expression here, 1, 2, 3 plus 4, 5, 6. And the computer spat out 3 numbers. And I thought, well, that's the end of that. And so I've been using this technology now for 35 years-ish. I started out in 1979 on a time sharing in those days was when you were sharing a computer, not a condo in Mexico. The customers were paying about $1 per CPU second on this machine, which was around the other side of the world in Toronto. I was using it from Oslo, Norway. And $1 per 1,000 characters of output that they received over the network. It's not as bad as it sounds, because it actually took several seconds for that to print out. So you were still getting some value for money. And now, so if we get to the recent end of my experience with APL, the last couple of things we've done is we've put out a Raspberry Pi version, which I think is significantly more powerful computer than the 360. Maybe doesn't have the same I/O capacity, but certainly things have changed a bit in this time. And last week we also released a version for the Mac. I see there are a few Macs here, so you can now get this and play with it on your Macs. So for me, it's been a love affair lasting a very long time. But of course, not everybody was keen on APL when they saw it for the first time. This is perhaps one. If you search on the internet, and there's still a lot of very old stuff you will find about APL. This is perhaps one of the most famous statements about APL. If you actually read up on it, you'll find that Dijkstra wasn't that sort of uniformly negative on APL. And anyway, I think there was a proposal that was it arrogance should be measured on a scale called the Dijkstra scale. But anyway, as you grow up and you learn to receive feedback from people, you learn how to read what people say. And there's parts of this that I really like. And you may be surprised. I like this last line here. I think being a coding bum is actually something that's a positive statement. You want to conserve your energy when you're writing code. Now, the history of APL is very long, and the language is quite different from other programming languages. And I think it's important to spend just a little bit of time looking at the man who invented it, who is passed away. I guess one of the few programming language creators. There's still only a handful who lived. He lived until he was 84 and passed away. It's not because he passed away young. So he was originally on a farm, and he went to one-room school. He did 9 years of schooling and went back to the farm. And that could have been the end of it if it hadn't been for being drafted by the army. So whatever you think of the army, at least in this case, turned out to be a very good thing, that they drafted Ken. And he almost finished high school in the service, and he found that he really enjoyed mathematics and teaching it to his fellow soldiers. And they told him that if he didn't go back to university after the war, they were going to come and beat him up. So he had to do that. So he embarked on an academic career, which became quite an interesting one. He did doctoral work at Harvard with Aiken and Leontief, who later won the Nobel Prize in Economics for his input-output matrices, which I think also recognized as a very early precursor of some of the algorithms in the Google PageRanking, from what I was able to read yesterday when I was researching that. But he taught at Harvard. He was teaching mathematics after doing this work, and he was really getting frustrated with what he felt was the inadequacy of mathematical notation. And he developed his own notation, wrote a book about it in 1962. But people at Harvard said, well, all you've done is publish that little book, and they didn't grant him tenure. And he moved off to IBM to work with people there who then, after APL had been used to teach mathematics and matrix algebra for some years, implemented the first interpreter for the language. So the language was initially designed as a communication tool for humans and used in that way on blackboards for some years before the first interpreter was created. And of course, for that little book, Iverson did later receive the Turing Award for his pioneering work in education, in time sharing, and so on. So here's what was really winding Ken up, especially when he was doing the work on mathematics. He found that mathematics had all these strange forms. There was, a very wide variety of syntactical forms. There were very strange and inconsistent precedence rules. What order do you do the suffixes and so on. And when particularly when he was working with matrices, it was pretty frustrating. And so he came up with this language which has a very small amount of different syntaxes, but rather than look at the PowerPoint, I'm going to do some live coding. Most of the interesting parts of this presentation will hopefully be the live coding. So those of you who can't read this, it may be worth coming over here, because I think at least half the time is going to be me typing expressions. Is that wrapping? Yeah, we had a bit of fun with the resolution here. Am I on? I'm in now, okay. So the first syntax you need is to be able to create a matrix. Arrays are fundamental to the language, and just by juxtaposing things, you create lists. So here we have a bunch of numbers, 3 scalars and a vector, and you can see the structure. The system, if you don't assign it to a variable, it just outputs the result of whatever expression you typed. You'll see me use this lamp symbol quite a lot. This is the lamp. It illuminates code. There's a lot of that kind of fun in the choice of symbols in APL. So this is an array of 2, we call them character vectors. You might call them strings. Arrays can be named. And of course, you can assign another name to something. And then we'll make a change to be here. And this is just to demonstrate that all the arrays in APL are value types, right? These are not reference arrays, but they are immutable, and they are all value types. So here's an array called form props, and this is really just to show you very briefly that we can do other things than calculations. We can create a form with those properties, and then you have an object model where the properties can be arrays, and I can set the caption, and I'm creating a list box inside, which I will set to have a background color. And I'm just going to do that so I can maintain a list of the different syntaxes as we go along here, since we're not looking at the PowerPoint. So after the array, the next form we have is a function followed by an array. So for example, iota6, the index generator, generates an array of the numbers up to 6. This little thing pointing down with a little step at the bottom is floor. The font size is just a little bit too big. Is it okay if I bring the font size down just a little bit? Yeah, okay. Yeah, we have lost a bit of real estate here. Okay, so item-wise map is implicit for all of what we call scalar functions, which is about half, at least half of the functions. So if you have an array, it just applies the function to every element of the array without you having to say map or for each or anything like that. So the exclamation mark standing before an array is factorial. And then we'll move on to the next syntax. There's only six or seven of these. The next one is a function with an array on both sides. We call that a dyadic or infix function. The first one we would call a monadic function. Unfortunately, we started using that terminology before monads were invented in functional programming, and it's a bit hard to. But I'm trying to use prefix and infix here to make it a little bit more palatable. So the thing that would have been ceiling, if you give it 2 arguments, it picks the largest of the 2 arguments. If you have the exclamation mark with something on both sides, it's related to the factorial. It's the binomial or the gamma function if they're floating point. We have division and so on and so forth. And of course, not everything works. We have errors, and the same if you try and divide a number by a character. That doesn't work. But here's this expression that made me fall in love with APL. 2 arrays, 1 function in the middle, and it just maps without you having to say anything. And it applies in the same way to virtually all of these functions, and also any functions that you might write yourself typically will just apply. Now, if there's not the same number on both sides, you get what we call a length error. But if there's exactly 1 number on the one side and an array on the other, we do something called scalar extension, and the single number is applied to all of the items. So far, we've only used lists. Here's a matrix. So this is the 2x4 reshape of iota 12. So that gives us, iota 8 would have been enough. I think I had a different example in mind when I started writing that line. And I can do matrix plus matrix, any rank. It all works exactly the same way. There's no different rules to learn as the rank increases. Writing rank invariant code is trivial. Right, so I'm just changing the print precision because I'm going to take the base 2 logarithm. So again, for a matrix on the right and a single number on the left, we can take the base 2 logarithm of all of these numbers. Now, not all of the functions are these scalar functions. So all the mathematical and logical functions are scalar, but the iota, if you give it 2 arguments, is a lookup. So it returns something with the same shape as the right argument, but it's looking each of the items up in the left. So it's still array-oriented, but it's not doing things a scalar at a time. Not everything is a scalar function. Right, and then we have again, slightly different terminology in APL. We distinguish between what we call functions and operators. An operator is something which typically takes a function as its operand. And the syntax there is you have a function preceding an operator. For example, plus reduce. The operator is on the right and it's acting on the plus. Again, I can name functions the same way I can name variables. So that gives me a function that does the plus reduction of an array. So plus reduce is the same as putting the plus function in between all the items of the arrays. I mean, for some of you who are doing functional programming, these concepts will be familiar, and they mostly came out of APL originally. A lot of the terminology was invented back in the late 50s and 60s. And all scalar functions apply in the same way. So anything that takes 2 arguments, you can do a reduction, and it's going to just do the work. There's also, if you turn the slash the other way, you get a scan, where it takes a prefix of a vector with 1 item, then 2 items, 3 items, 4 items, and does the reduction. So we have the accumulating sum if you use it with plus. And then the reduction also can take a left argument, which is the window size that you want to use. So you can say, I'd like to do the plus reduction of length 3 vectors. If we do a catenate reduction with the length 3, you can see that just catenates the items together and doesn't do an operation on them, and you can see the windows that were processed one by one. And then finally, we have the function, operator function, a dyadic operator that works on two functions, where the one that you'll all be familiar with is the vector product, so plus dot times inner product. So plus dot times is equivalent to the plus reduction of the map of times, so which is how you do a vector product, of course. But in APL, that's a completely general construct, so it's not just plus and times. In many tools like MATLAB or R, you'll have this thing extracted and presented as matrix product or vector product, a named function. But in APL, okay, this is just restating it the same way. In APL, it's completely general, so you could do an OR dot equals, which says are any of the items equals. So it maps the equals, and then it does an OR reduction. Okay, but that's nearly all the syntax there is. The only thing you need to remember when you're trying to parse this syntax is that there are no precedence rules, right? Iverson was wound up about all the different, when you do sine squared of x, what order are the operations done? So he picked this one, which he felt was sort of perhaps most representative of the general precedence, or this one was nice and easy anyway. And he said the argument to the function is the result of executing everything that's on the right. So this is the factorial of iota 6. So that there are no precedence rules. You just apply the function to the result of computing what's on the right. And if it's a dyadic function, then it essentially works in the same way, but the left arguments are also included. So if you were coming from another programming language and you looked at something like this, you might assume that it's going to do, that's 10 divided by 5 minus 1. But in APL, of course, it's 10 divided by 5 minus 1, and it doesn't give you the result you were thinking of. So remember that as you read the rest of this, if you can. And the final piece of syntax is an array, the square bracket indexing, which you would be familiar with from most languages. The thing that's slightly different about APL is that you can index with an array. So the indices can be arrays. I think you do see that in some other languages. So the shape of the result has the same shape as the index array rather than the data that's being indexed. Of course, once functional programming become better understood, most of APL predates really an understanding of what functional programming was. So in 1984, it was decided that there should be a function where comprised by overstriking the two square brackets, the squad indexing, so that you could do indexing in a functional style. Okay, so if you're if this has whetted your appetite at all, there's a website called tryapl.org where you can type your APL expressions, and there's an APL keyboard that pops up if you need it. And there's a primer page where you can hover over each one. I mean, this list here is all that there is to learn about the language, right? It may look a bit intimidating with the squiggles, but there's not that much to learn. You can hover over these in tryapl and you can see the definition of each one. And in the Windows product and on the Mac, we have this language bar where you can hover over the symbols and you can get the definitions. We run a programming competition for students each year, and we had the winner one year say, well, he would read the problem description and then he would just hover with the mouse slowly from left to right until he saw how to solve the problem. And that was all the documentation he needed. So if your brain clicks when you see this array notation, there's these 6 rules and there's 40 functions, and off you go. Of course, there's more to building applications than that. But right, so briefly back to PowerPoint, unfortunately. So we've looked at that. So just to recap the fundamentals, there's only one data type in APL, the immutable array. There's a little star there that we'll get to at the bottom of the slide, each item is either a number or a character or another array. For example, a single number is a zero-dimensional array, but it's still considered an array. It's not a different type. There isn't different syntax to deal with it. For most primitive functions, map is implicit. The functions are either prefix or infix, but the operators are either postfix or infix. And I don't know how Iverson and his compatriots, when they were designing the language, came up with that, but there's something magical about this interplay between the functions being prefix and the operators postfix when you're designing a DSL. So writing an embedded DSL is typically how a lot of APL application development is done, with the end user sort of synthesizing their own functions from these building blocks. The order of execution we looked at, and here's the little star. We added, at least in Dyalog APL, we added the ability to have objects. So like these forms, like .NET objects or other types of external objects. And of course, once you have an item in an array which is an object, you lose the immutability, because if that thing is a reference type, and there's not much, we're not going to copy them when we copy the arrays. So how did this work then in the end? He had this list and he came up with a new notation, and let's organize them and see. Okay, so that's A times B. That's the e to the power x, no left argument, and the power function means e to the power, x divided by y, the base b logarithm of a. Notice the symbol is a log seen edgewise, at the same time as it's clearly related to this one, right? So there's a lot of that kind of mnemonic stuff to help you learn the language. The nth root is a to the power reciprocal of n. Matrix multiplication is like vector multiplication. If you have two matrices, it just does the vector product on the columns on the one side and the row on the other. Fgx is fgx, the third trigonometric function, squared. Sigmas and pi's are easily expressed using plus reduce something times iota something. And okay, there isn't going to be room to the right of this one, but it still maps. I mean, if you're accustomed to mathematical notation, the translation of this into that is not a very difficult thing. And once you have experience with the language, although it clearly executes from right to left, we would say you read it from left to right. So to read that statement there, you would say, well, it's 2 times a divided into minus b plus or minus the square root of b squared minus 4ac, which is probably how you would read the math as well. And if you're writing good APL code, at least in my group, if you can't read it from left to right, you should probably split the function up. But that's something that, there are different opinions about that, of course. Okay, so APL was sort of instrumental in discovering functional programming. And John Backus, the inventor, I think, of Fortran and Backus Nauer form, in his Turing Award lecture, recognized Ken's work. But he did go on to say, he wasn't quite as unhappy as Dijkstra, of course. But he was still unhappy with the fact that there was the world of expressions and statements, and there were only these 3 functional forms. There were actually 4. He missed scan. But since then, that was in 1977. So APL today, although many people equate APL with, they learned it once, they did some work in a bank in the 70s or 80s, and they're not aware of the work that's been done since then. So we have new functional forms. We have ways of defining functions in a lexical style, a functional lexical style. So the first function here is the definition of the average. Omega is a reference to the right argument. So if you have a function that just references omega, it's a prefix function. The next one, plus double, is an infix function because it references both alpha, the left argument, and omega. And then the Fibonacci function there is a multi-line function. The omega equals 0 is a guard, so it says if this is true, then the result is simply that. Otherwise, it continues, and the del is a recursion, so it's calling itself again. Let's see. How are we doing for time? Yeah, so there's a whole bunch of functional forms. We're going to be using some of these, so I won't really go into them now, but let's go back and look at one of the new functional forms that I think is kind of fun, that wasn't there when Backus was looking at it. So here's a function, 1 plus the reciprocal of the right argument. So it returns 2. If you apply it twice and 3 times, it's heading towards the golden ratio, for those of you who recognize the math. Now, it gets a bit tedious if you have to do that again and again. So there's a power operator, which you see is a very similar symbol to the mathematical exponentiation. It just has a diaresis above it, where you can say, well, repeat the function, in this case, 4 times, 5 times, or create a little lambda function which takes the right argument and applies it that many times, and apply that each to iota 10. And you can see we're getting closer and closer to the golden ratio. But then there's an extension to it where if the right operand is not a number but a function, then that function is applied between successive results, and the iteration terminates when it returns true. So this will continue until we get to the fixed point and we have the golden ratio. Let's see, I think we're running a little bit. I'm talking too much as always, so I'm going to skip over a little bit here. We saw an example of a user-defined, we'll see a slide with some user-defined operators. So you can write user-defined operators using the same curly bracket notation, but you refer to the operands as alpha, alpha, and omega, omega. Works pretty much the same way. So in addition to these new functional forms, and we'll see them, if I don't talk too much, we'll see pretty much all of them in some live code a little bit later. Okay, here's a slide with there's a postfix operator because it refers only to alpha, alpha, and a dyadic or infix operator referring both to alpha, alpha, and omega, omega. But I don't really have time to spend as much time on that as I hope. Anyway, so there's a gap here. You notice there's a big hole in the middle because there was one thing that Iverson couldn't figure out how to get a good notation for in APL. And that's the mathematical notation where you're adding 2 functions together, which in math you would write f plus g in parentheses of x. And the story goes that he's been searching for this for a couple of decades. Arthur may know more of that story than I do. And then on the plane on the way back from an APL conference in Australia, he woke up, the sun came through the window, and he realized that the solution was just to write f plus g x, because that was a syntax error in APL. You can't have a train of 3 functions with no argument if you put them in parentheses. So that was exactly the syntax he was looking for. But of course, being Iverson, he wasn't satisfied to have a syntax for f plus g. He's thinking that, well, it could be any 3 functions. So there's a general definition of a train of 3 functions. FGH, that gives you a function which, if it has a right argument, it's f of x and h of x, so the 2 functions on either side, and then the result is piped into the middle function, which is why that's referred to as a fork, because it's bringing the functions together to the central function. And if it's dyadic, it extends the same way, and then you can also have a definition for a train of 2 functions together, which is just, it's called a top, but it's really just a fork that only has one arm. So are those useful, or is it just... What have I done? Here we go. Okay, so we've seen the definition. Well, it turns out that something quite as ordinary as the average is a fork, because the average is the sum divided by the count. So plus reduce, divide, and the function called tally, you can see that it's a four-fingered animal, I guess, counting 1, 2, 3, 4, the symbol for tally. And there you are. And you can also take derived functions, so the max reduce and the min reduce and the comma in between is also a fork. And in fact, they extend, the notation is such that they nest from the right, so that's the plus reduce forked with the fork defined by max reduce and min reduce. So you can get this syntax where you can say, well, give me the maximum, give me the sum, give me the maximum, and give me the minimum. It's not actually an array of functions, but when you use it this way, it has that, it works as that kind of notation. So let's see, how are we doing for time? Right. Now, the original title of this talk was Pragmatic Functional Programming. How many people here would say they are functional programmers? There's not that many. So it may not. I have a little section here where I show the APL equivalents of scheme examples and so on. Maybe I'll skip that the live code, since there was only, I think, 3 people who put their hands up. But as you can see, from I think we've seen most of these in the live code already. Most of the classical functional forms from a language like Scheme have very simple equivalents in APL. Juxtaposition creates lists, and so on. And you're not Scheme programmers, so I'll skip over that one as well. One of the things, though, that I think I do want to spend some time on is sort of talking about how APL really, when you write code, idiomatic code in APL, it generalizes to higher ranks. It's rank invariant code. So in Scheme, the definition of a vector product and the matrix multiplication are, quite different. There's a lot more code there in the matrix form. Let's see if I can find this. Okay. So if you take, here's a function, the question mark 6, do it again. Any guesses for what this does? Generates random numbers. The right argument gives you the range of integers. Now if you pass it an array, it then applies that. So now we've rolled 4 dice. This reshape function can be used to generate an array of any rank and shape. So the 10 reshape of 6 gives you 10 6s. So I can say I want to roll 10 dice using this expression. Now I'm setting the random seed here so that I get some numbers that are going to work for the next few lines of code. So I roll 10 dice, and now I want to do some analysis. So we haven't really seen any logical functions yet, but they also work in the same way. They are all scalar functions. So throws equals 5 returns, well, you might expect some kind of Boolean array, and in fact APL programmers call this a Boolean array, but actually it's a 1-bit integer. We have 1-bit integers, 8-bit, 16, 32-bit integers in the implementation. And the nice thing about them being integers is that they're in the domain of all the mathematical functions. So if I want to know how many throws were equal to 5, I can just write this expression. And I can use this outer product thing to do a whole bunch of comparisons. So outer product takes all the items on the left and all the items on the right, and combines them using the function. The null dot is the outer product, and the equals is the function that you're applying. So I can find out how many there were of each one of the 6 alternatives by writing plus reduce iota 6 null dot equals and my throws. And now I'm generating I'm rolling 1,000,000 dice with the same expression. And you can see that doesn't take, well, I mean, on a modern computer, you might not expect that to take time, but in an interpreted language, you might think it would take significant time. But of course, there's virtually no interpretation going on here. You can almost think of the APL expression as bytecode, right? It's diving straight into highly optimized C code that's using the 1 byte integer data type because the range is 6, and it can do this extremely fast. And if you build user-defined functions based on the APL primitives, of course, without really having to do anything, so I say the square root is omega to the power 0.5, I have a function which is also rank invariant because it's just passing those arrays to primitive functions. I can call it on our 2x4 mat that we defined earlier. And I can define the hypotenuse as the square root of the inner product with power. So I take the left argument, the right argument, I square them, and I do a plus reduction of the result of that. And I take the square root, so the hypotenuse is 5, print precision 6. But again, this function just applies without me having to write any loops. It would apply to arguments of higher ranks. And in fact, I can use, as I said, if you have a dyadic user-defined function, it can be used with most of these operators in the same way as a primitive. So this is the plus dot hypotenuse. So it's the plus reduction of the hypotenuse map on these vectors. So you can combine, and that's some people, if you're coming from a typical software engineering background, you'll say, well, this business that APL can only have left argument and right argument, right? You're going to need more arguments, 3 arguments, 4 arguments. But as soon as you allow that, then the beauty of these operations, the mathematical operations, collapses, and you end up in a language which has lots of parentheses and stuff and can do more stuff, right? But isn't a tool of thought for non-software engineer users, which is where most of the really successful APL users are coming from. Sort of any kind of engineer other than a software engineer. And the inner product is also carefully designed to extend to higher rank. So here we have a vector plus dot times. But if we have our matrix, then we can say matrix plus dot times and a vector, and that'll do the plus dot times, taking each vector on the left and reusing the single vector which is available on the right. Mat or dot equals 7. The 7 is extended to a vector and then reused, and we can find out if any of the rows of the matrix contain a 7. We can make ourselves, the first symbol there is transpose. So make a 3x4 matrix with those rows and then turn them into columns. So we have a matrix variable with 2 rows and a coefficients matrix with 3 columns. And then matrix multiplication is still the same symbol, plus dot times, because it's just cycling through the rows on the left and the columns on the right. Ooh, 3 dimensions. A unary minus. Oh, good question. So it's the high minus. I should have mentioned that. Yes, in APL, the normal low minus is a function. It's a prefixed function that applies to the whole array. So APL has to use a different symbol for entering negative constants. So we use the high minus for that. Sorry, I should have mentioned that. It's just second nature and forgotten 30 years ago. Good question. Yep.
Just a reminder, if people ask questions, either repeat it or
Yep.
let me give them a mic.
Yep, okay. So I'll try to remember that next time. So here's a cube, 2 by 3 by 4, reshape of iota 24. Now, say we wanted, well, we can do the plus reduction of cube, right? That works on the vectors as it did before. So we had a 2 by 3, oops, I thought I'd shut Outlook down. Just a sec while I do that. This is a remnant of when we were setting up the Hangout. So we have a 2 by 3 by 4 matrix. We do a plus reduction. We lose the last dimension. We get a 2 by 3 array back, which is the sum of each one of the rows. We have a slash with a bar through it, which says do the plus reduction, but doing it on the leading dimension. So it's going to be doing the plus reduction down through the planes, so we get the sum of the two planes. And of course, if it's n-dimensional, we can't keep adding symbols for all the cases. We have a special symbol for the first and last dimension, but you can also, in brackets, this is a slight anomalous syntax, but we can direct the reduction to go along a particular dimension, in this case, go down the columns. Now, so the tally is the length of the leading dimension, so that's 2 in this case. If we define our average function as the sum along the leading dimension divided by the tally, which is the length of the leading dimension, then it still works with a vector because that just has one dimension, so that's fine. And yeah, I'm sorry, the resolution has changed a bit here. But the average on the cube is now going along the first dimension. So it's summing the planes and dividing by the number of planes. But there's a nice interaction with one of the newer operators that's been added since Backus time. There's a rank operator. So we can say apply the function average rank 1, which means split the argument array into subarrays of rank 1. So in this case, we would get a 2 by 3 frame of vectors and compute the averages. So the average function is applied to each row. And that gives you, not surprisingly, the average of each one of those rows. What's interesting is if you take this function, which is written to compute the average along the leading dimension, and you apply it rank 2, that means you're passing to that function a matrix each time. So you take the rank 2 subarrays, of which there are 2. Each one is 3 by 4. And you pass the average function to that, and you can compute the average of the columns. And then if you pass it rank 3, that's, in this case, since it's 3-dimensional, that's the same as passing it the original array, and it does the computation on the first dimension. So using this rank conjunction, or operator, we can compute the average along any one of the dimensions of the array using that same piece of code. Question? Yeah?
How do you go about unshaping the cube and averaging over all the numbers instead of dimensions?
If you wanted to average all the numbers, the comma, sorry, the question is how do I average all of the numbers in the cube without regard to the structure of the cube? What I would do then is use a function called REPL. The comma, prefixed comma, simply removes all structure from an array. So the average of cube would be that. Yeah. Or of course you could apply average repeatedly, losing a dimension. Well, yeah, in this case that would work, but that's not a safe technique always. Okay. Now, one of the things, the fact that the functions all map implicitly allows you to do is write what I would call sort of switch-free logic. So if I have some data here, 4-element array, and I wanted to pick an item of the array if it was greater than 5, but if it was less than 5, I wanted the value 5 instead. Then in a traditional programming language, I would have written something like if data sub I, you make a loop, and then if the element is greater than 5, keep it, otherwise return something else. But in APL, you would just say data max 5. And if element by element, it would pick the greatest of 5 and the corresponding item of the array. Let me get rid of this. Now, if we wanted to, for example, increment each item of data depending on whether it lived up to some condition. So we said if the item is an element of this list, then increment it by 1, otherwise leave it as it is. Then in APL, you can say data plus data element 3715, because data element 3715 returns an array of the same shape as the left argument for each item telling you whether it's a member of the set provided as the right argument, and that Boolean array can just be added to the original data. So if I wanted to add 2 in for each case, then I would say data plus 2 times data is an element of something. And I don't know how many people here write CUDA code or GPU code, because I've been told that the kind of code you need to write there, where you have a bunch of processes executing in lockstep, is very similar to writing code like this. And you can also merge, so I've got 2 arrays here, x and y. X is 1, 2, 3, 4. Y is 10, 20, 30, 40. And I want to pick x if the flag is true, or I want to pick the corresponding element of y if it's false. Then I would say x times flags plus y times not flags, and I can implement again. I can do a lot of parallel processing without writing loops. Okay. So you might say, well, if this stuff is so wonderful, where have we all been? How many people here had heard of APL? Oh, you had? Okay, so I should have asked at the beginning what you had heard. But one of the reasons you generally, at least as a software engineer, hear very little about APL is that the successful APL users, I would claim, are people who are as I said before, any kind of engineer other than a software engineer. So they don't really feel comfortable discussing programming. They're solving some kind of actuarial problem or chemical engineering problem. They don't go to software conferences. They absolutely hate it when they have to change the way that they do things. So when the PC came along and they were using APL on the mainframe, they said, well, what is the advantage of this? I have to take my own backups. If it breaks, it's my own problem. And a lot of the usage of APL simply died with the mainframe because the people didn't realize that the technology were changing underfoot. And then we came into this really dark period. I think even for people who were software engineers, this was a very difficult time where the APIs were changing, and where APL programmers had been able to write actually pretty nice user interfaces and so on the mainframe, they suddenly had to, try and adapt to all these software engineering paradigms that meant nothing to them. And they really, struggled a lot in that period. Fortunately, I would say this seems to have been temporary. The new APIs that are coming out now, the more object-oriented frameworks like the .NET framework, the Java frameworks, self-describing systems that can be used in very much the same way as APL programmers are used to. They've got reflection, they can type expressions and experiment and so on. It looks like we can start providing APL users again with tools for building user interfaces, web-based interfaces, for example, that they will be able to use. And of course, the focus in the rest of the community on functional programming and the need to take use of parallel hardware, which is appearing everywhere, is giving us, I think, some courage to reappear. Functional programming took about 80 years to catch on from the first ideas were mentioned. Object-oriented programming, probably about 20 from Simula until Xerox started using it really with with Smalltalk and so on. Arrays are now about 50 years old. If you want to successfully build a group to use APL, I would say you need the right mix of domain experts and software engineers, right? You can't just do with the domain experts because they'll build things that will break. But you need to allow them the freedom to experiment with writing applications. Be pragmatic. We encourage a functional style of programming, but we don't demand it. And what we're starting to think, I think, is that languages like APL, maybe not APL itself, maybe something there, Google will invent that will embed some of these ideas, will be the solution to the next big problem after concurrency, which is simply complexity. You need much more powerful tools where the domain experts can bring their knowledge to bear directly on the data. Because if they have to explain it, even using agile techniques, to somebody, it's already too late. There are some customers or some organizations who are happy to talk about the fact that they use APL. Typically, they're either sort of slightly embarrassed by using this really left field technology, or they consider it to be a secret weapon that they don't want to talk about because it increases their productivity so much that they'd rather not talk about it for that reason. But there are quite a few people using it to build some very significant applications. So, I mean, it's been 50 years, 52 years, I think. A lot of the early criticism of APL, I think, was quite valid, and we've been working hard on addressing a lot of it. Today, our elevator pitch is this text that's up on the screen now. We would say we are an array-first multi-paradigm programming language. So we also support, functional styles. We have object orientation. You can create classes that can be used in external object-oriented frameworks, etc. But it's still very much based on an APL language kernel. And I do need to spend 1 minute on this one. So you might think, if you were using Scheme or some other similar language, that these two expressions are logically equivalent, right? In fact, the first one's better because it consists of English language statements that people can easily relate to, whereas the one at the bottom is a pretty weird-looking mathematical statement. But once you get used to using APL and you look at that second statement there, you think, hang on, but that's just the plus reduce iota each of iota 6. So I can blend those two together. And of course, the plus reduce of the first n integers is really just the argument plus times 1 plus the argument divided by 2 applied to each one of those functions. And when you've looked at that for a little while, you realize that that's actually just the plus scan of iota of the first 6. But sometimes you need to be experimenting interactively with these things before it's easy to see these. But our experience is, at least the people who do get used to this, it's really worthwhile learning the symbols and being able to apply what you learned in school, doing math, physics, whatever, directly in your programming. Okay, so I'd better... Oh, well, since Arthur's here, I really want to show you this one also, because this is one of my favorite quotes by Arthur Whitney here, the inventor of the K language. I think this is very, very true. Very, very true statement. And I think I'll leave it there and take some questions. Yes?
What is 0.1 plus
0.1 plus 0.2. The question is, what is 0.1 plus 0.2? It's 0.3.
Are those doubles?
Well, APL APL really only recognizes numbers. And it's doing everything it can to hide the fact that it might be using a variety of different internal representations from you. So if an array, you compute something and it collapses to all zeros, then you end up with one of these Boolean arrays, a bit per element. And in fact, the interpreter spends quite a lot of time trying to collapse data types. As it runs, it will occasionally see whether it can collapse down to a smaller data type. But the illusion that we're trying to preserve is that as a mathematical notation, we just have numbers. We don't really recognize numeric types. Yeah.
So this is a really, really nice notation for linear algebra. So this is a nice notation for linear algebra and stuff that's sort of isomorphic to linear algebra. Mm-hmm. Could we expand this onto more abstract algebra? Like, could I do this computation over like a monoid or a ring? Because that would be really nice for my software engineering. Or has anybody thought about this stuff?
I don't know. Sorry, a monoid?
Operator, or you have a set with a closed operator that's associated and has an identity. So like lists and strings and max and integers and.
No, I mean I think people did look at that early on. People who also are using other programming languages. Today, the usage is really focused on numerical applications and data mining applications and so on, where you're doing a lot of number crunching. So I don't have a good answer to that question. Yeah.
You said you're mainly focused on numeric applications. So, but I'd still like to know how do you deal with promotion of when an overflow occurs? And in this case, you're probably not using a double or an I3 floating point. So yeah, the question is when do you use big decimal and fixed precision stuff and floating precision stuff? How do you choose that?
Yeah, if you want to go to decimal, higher, we also support quadruple precision decimal, the IEEE format. But that is a conscious choice by the user. They have to say, I want to have much higher precision decimals because those have a very significant cost associated with them. But normally we go through 1-bit, 8-bit integers, 16, 32-bit integers. We'll blow up into doubles, and we also consider complex numbers to be in that continuum of numeric representations. And that's all done completely automatically. You can influence it, but generally that's frowned upon. You might do that if you need to cast a type to pass it to some C program or something like that. But generally in an APL program, you wouldn't do that. Yeah. Oh.
I've got a few questions from remote offices.
Okay.
So has APL been used on large data sets that require techniques such as sharding?
Yes, it certainly has by some of those customers. But it's not something that we provide support for at the moment natively in the language. Other than that, you can map any array to an array to a mapped file. But at the language level, we don't provide tools to deal directly with sharding.
Do you have any crazy one-liners to show?
Well, I mean, there was the one that Russ sent out in the invitation. I don't know how crazy it is. Let's see, can we find it? Right, this expression for finding all the primes between 1 and r. Which is also, it's one of those things that I don't know where this image came from, but it's sort of an example of really bad APL code from the early days, because it modifies, you're modifying the right argument. The first thing you do in this expression is you take r and you reassign it to the one drop of something. And today that would be, you would want to write it as one of these lexically scoped things where that temporary array you needed was a local variable. But I mean, do you want an explanation of how that works? Or, I mean, it's quite simple. So, no? Basically, it's doing an outer product. All the numbers between 1 and r, it's multiplying them, doing the outer product, doing all the multiplications. and then seeing whether the number is an element of all of those products of everything. So it's a very direct expression of what it means for something to be prime, but of course it's hideously inefficient. Although it's so short that you could, at the interpreter level, you could recognize that as an idiom and say, well, the guy's obviously trying to compute the prime numbers. And that's one of the advantages of this notation. If you think about that example in Scheme with the plus reduction and so on, I think the classical thinking today is you write that kind of expression, and then some very clever optimizing compiler is going to detect the loops within loops, and it's going to fuse them and get rid of them. Whereas in APL, you have these much higher level constructions that even an interpreter can optimize. You don't actually need, we also want to do loop fusion and stuff, and we're working on writing a compiler. But it's much easier to write highly optimized idiom recognition in APL than I think it is in most languages.
Another question from remote office. I've thought that something like APL in its environment is what spreadsheets should have been like. Comments?
What spreadsheets should have been like? I think a lot of the earliest spreadsheets on mainframes were actually implemented in APL by APL users. But spreadsheets provide much more than APL does. Right? APL is a programming language, whereas the spreadsheets have formatting and very simple ways of storing data built into this package. Right, so it's sort of a mashup kind of thing. I think that there are quite a few applications where people would prototype them in a spreadsheet and then rewrite them in APL because they needed more structure, right? Spreadsheets are incredibly dangerous things because you can overtype an expression and you realize 10 years later that you haven't actually been recomputing that value. Whereas APL gives you a lot of the same features as a spreadsheet, but it does require you to be a bit more disciplined and do a bit more work. Yeah.
So I have two questions. I'll let you decide which of them you want to answer, or both. I was wondering if you could say something, especially perhaps since Arthur is here, about the relationship between APL and J and K, and when one would look at to one or the other. Why would I learn APL versus J or K? A different question, which is similar, is for people who are less familiar with these array-based languages, why would I look at this these days versus something like R or MATLAB or Mathematica?
Yeah. Maybe do the last one first. Why APL rather than R or Mathematica or MATLAB? I mean, those tools have all been extremely successful, but I think not due to the beauty of the programming language, right? It's more that they have collected extremely good libraries, and they've managed to present them in a way where people, engineers who needed to solve problem very, very quickly found the things that they needed for whatever application they were doing. You could solve 95% of what you needed with standard libraries. But when you need to go beyond what the standard libraries can do, that's where I think, APL, the users that we have are typically people who are operating outside the 90%. They have new ideas about calculations that aren't available in those packages. I think APL could be a really good future implementation language for many of those packages. I sort of understand why they didn't use APL when they started those products back in the 90s, where the APL interpreters really weren't up to it. Today, I think it might be different if they were starting again. A lot of those people did come out of APL. On the question of when would you use K versus J versus APL? That's very difficult. Clearly, K, if you're doing anything that has to do with really large volumes of data and real-time trading, they would run rings around an APL interpreter. I think APL products, certainly like ours, have much more capability in terms of interfaces to .NET. We allow you to create classes that can be consumed directly by C#. We have interfaces to databases, and much more of a general purpose programming language. I think better debugging tools, I would say, at least at the moment. Same is probably true for J. With J, I would say we're actually at the moment in the process of adopting a lot of the language features that were put into J. J is sort of like an increased instruction set APL system, whereas I think, I mean, Arthur, correct me if I'm wrong, I would say K is really a RISC APL system, right? We only need this and throw out the stuff that is sort of bloat and make it run really, really fast on humongous data. Is that fair? Yep. Yeah. We're sort of the general purpose tool. J is very focused on teaching, so they have fantastic mathematical labs and examples of how to do math. Yeah, Russ?
What community contributed libraries are there?
That's really one of the weak points of the language as it stands today, and one of the things that we see as our biggest challenge for the next few years. We've been building, and I'm talking about Dyalog specifically, we've been building frameworks to deal with source code in Unicode files rather than the binary formats that APL has typically used in the past. And we're really trying to construct an environment where we will see much more user participation in terms of building libraries than we've seen in the past. Typically, APL vendors have provided nearly all the libraries in the past, and that's a weakness. And it has a lot to do with what I mentioned before, that the APL users aren't really motivated, right? They're not software engineers. They're trying to price a new insurance product to sell next week, and when they've done that, their boss is going to give them another problem to solve. And they're not really, Python and these languages which have some similarity to APL have, I think, a larger traditional software engineering part of the community, which means they've been better at building that kind of thing. Yeah. All your symbols are in Unicode? Sorry? All the symbols are in Unicode, yeah, and have been, they were in Unicode 1.0. Yeah, so that's Unicode has been so good for us. We just use Subversion or whatever. The latest thing is we're moving to Git, like everybody else. And it's just Unicode. Even all the diff tools out there just work with APL now. You don't have to do anything. Everything just works. Yeah. Okay, I'm not sure. Yeah, go ahead.
Oh, so about the user libraries.
Yeah.
User-generated libraries or user contributions to the language.
Yeah.
You said you guys have been.
Yes. Working on tools to make APL development much more similar to traditional development. So using source code management systems, dependency management tools, build tools that everybody else is using. Whereas in the past, APL programmers have tended to, or the large APL shops would all build their own source code management tools where the data was stored in, like spreadsheets, binary proprietary formats from the various vendors. But that's really changing, and we can see the new people coming into APL today compared to the guys who started, there was this big wave of people who started using APL in the 70s and 80s, and then as the market faded when the mainframe died, those people carried on being the main contributors, and they really didn't have a modern way of approaching software development. We can now see we have a second wave of people coming into the language who have a very different approach, and will probably change things quite dramatically over the next 5 years for how APL is used.
So the other language that I've used, or the only language that I've used that's really significantly Unicode-y in its operators is Agda. And it has this really, really lovely Emacs mode where you can type right arrow and then it'll insert a little right arrow for you. Mm-hmm. Is there something like that so I could write APL in a text editor or a terminal or something that's not an APL IDE?
There are at least a couple of Emacs modes out there if you search for them. Or send me an email and I'll give you links to people. We are in the process of, we just released this Mac version last week, and that's using a completely new IDE. We've had this Windows product for a decade where nearly all the users have been, which is very much a Win32 application. But we've now separated the interpreter from these data streams, and we're in the process of publishing them. And it'll be possible for anybody to write a front end to APL in about another year when we finally finalize that format. And then it'll become very easy to write plugins for Emacs, Eclipse, whatever you want. Yeah, but we do already have some people who've built Emacs modes. Yeah.
I'm told that Iverson originally intended to have APL to natively apply to arrays and trees. What happened to the latter?
What happened to the trees, Arthur? I don't know. I mean, the nested arrays were added in 1983, right? Before 1983, all the arrays were just rectangular, flat arrays that had to consist entirely of numbers or characters. And then there was this thing called APL2, which came along from IBM in 1984, where anything could become, any element of an array could be another array. And at that point, I think a lot of people were thinking about things to traverse trees, because clearly if you can have nested arrays, you can have trees. I think possibly a part of the problem is that the efficiency is a problem, right? Because you can write a very highly optimized APL or K or J interpreter. When it's working on flat arrays, it can actually outperform hand-coded C because it knows things about how you're combining operations. Or it's better than the hand-coded C that you would normally write, because you'd have to go to superhuman efforts to beat it. Of course, hand-coded C can always beat an APL interpreter. But I think on trees, because you would typically be recursively going through a structure where there's a lot more pointers and so on, you need a compiler to get really efficient tree traversal, at least if the trees have small nodes. I don't know, what do you say, Arthur?
Yeah, I hadn't heard that.
I've read a lot of Iverson stuff.
Yeah, no, that's definitely the case. That
Yes. Okay, so I don't know.
Ken had, I think in the APL book, there were ideas for notation for tree traversal and so on. Yeah. It was called APL, a programming language, which seems strange today to software engineers, of course, because it doesn't look like a programming language. But of course, he was doing math, right? And so for him, the choice of words, Ken was always very careful with his words. It was exactly right. It was for programming steps of mathematical operations.
So I've looked at some tree stuff in J, and I think some of the challenges are that a lot of tree operations are incremental, whereas array languages like to operate on the entire data set at a time, right? And so when you break it up into smaller operations, then you kind of get the interpreted overhead coming in a little bit.
Yeah, I think that's sort of what I was trying to say, yeah. I agree, that's a challenge. Now, of course, we are working, I don't know about the other APL vendors, but we're working quite hard on compilers now. And I think Arthur is also thinking about compilers. There have been several attempts through the ages to write compilers for APL, but they have, on hardware, 20 years ago, they rarely succeeded in speeding things up by more than a factor of 2. And people couldn't be bothered they wouldn't accept the inconvenience of a compiler compared to this, inalienable, dynamic, interactive way of life for a factor of 2 improvement. But today, the way the hardware is changing, where you have all this concurrency and the speed of the CPU relative to the speed of the memory has changed dramatically in the last decade, right? The memory isn't getting any faster, or not much faster, but they can do all kinds of crazy clever stuff inside the chips. So the win from creating a compiler today could be orders of magnitude speed up rather than just that factor of 2 that they were able to achieve before. So there's several people working now on compilers, I think. And then we can get back into trees and extend the notation to do tree traversal. Here's something that one of our customers has built in APL. There you go. It's finished. Yep. Okay. It's only another few seconds. We're getting some feedback. Anyway. So this is the result of an initiative in Finland where the government decided to make all of this 3D map data available free of charge to everybody, and they launched a competition for the best application to take advantage of it. And one of our users built this. It's a game that he sells to private individuals and to the search and rescue operations in Finland. So we're out of time. So no, we've had questions, and maybe I'll just leave that one up. If you want to get hold of it, try APL. They're free versions available for students. If anybody here is really interested, drop me a line, and I'm sure we can get you a copy. So that's it. Thank you very much for listening.